Welcome back. I'm Professor Andy Gunawardena, and today we're going to discuss an exciting topic called classification through logistic regression. So, what is classification with logistic regression? It's a method used to predict categorical outcomes, typically binary, by modeling the probability that an instance belongs to a particular class. This approach is commonly applied in scenarios such as determining whether an email is a spam or not, or predicting the likelihood of a disease being present, or any situation where outcome is categorical. Logistic regression is straightforward, interpretable, and effective for many binary classification problems. So let's compare logistic regression and classification. Linear regression models a function that maps features represented by x with d dimensions to a real number output y. In this process, we are finding a function that fits the training data well, making it possible to predict continuous values based on our input features. Classification, similar to regression, predicts an output y, but here the y is categorical. In binary classification, y can take one of two values, such as -1 or +1 or 0 or 1. In multi-class classification, y can belong to one of the multiple classes from 1 to k, where k is the number of categories. For example, we can take a bunch of articles and classify them to be into 3 categories as shown here. So there are many applications. Classification helps in machine learning make decisions based on categories. For example, email classification distinguishes between spam and not spam. E-commerce transaction can detect fraud and not fraud. Or tumor classification determines if a tumor is benign or malignant. Often we use encoding to represent categories numerically, like assigning negative a value of 0 and a positive a value of 1, making it easier for algorithms to process these distinctions. A well-known application of classification in machine learning is diagnosing whether a breast tumor is benign or malignant. As studied by Street, in this setting, a doctor extracts a fluid sample from the tumor, stains the cells, and outlines them, often with the aid of an image processing to refine the outline. The system then computes several features for each cell, such as area, perimeter, concavity, and texture. For these features, it calculates statistics like mean, standard deviation, and maximum values to help make an accurate diagnosis. So here's a breast cancer dataset. It contains many features that can be used to predict if a tumor is malignant or benign. First, we have to learn from the data what features can help predict y, to be 0 for malignant or 1 for benign. Of course, we can use all the features, but that would be computationally expensive. So first, let's find out if there are some features that are more predictive than the others. Say, for example, we plot only the mean area and mean number of concave points and color code cells as red or blue. There seems to be a clear divide in benign and malignant tumors. Hence, these two features can be a good predictor. We can certainly add more features to increase the predictive power, but for now, we'll stick with the two features. Now the question comes to is how can we find a line that separates the two types of tumors? We need to develop a mathematical model to understand it. So the problem comes down to determining the boundary that separates two types. So let's just guess the equation of the separation line is h theta x is -8 plus 16x1 plus 10x2. And if you plug in the points x1 equals 0.8 and x2 equals 1, we get h theta x to be greater than 0. And if you have another observation, 0.2 and 0.4, h theta x is less than 0. So we say that the first point is going to be a yellow group, and the second point will be here, below the line h theta x. So this is the line where h theta x is 0. So the question comes to, how can we determine the separating boundary h theta x? So here's another example where we can predict the pass-fail status based on where the separation line is. So here, if you can draw the line to show the separation, then we can see that. You'll see that we won't be able to draw a perfect line here, but we can do it in the best case possible. So let's develop some notation. We denote the input features by xi, and there are m input observations. We also have m input labels, observed labels. The goal is to find the theta parameters by minimizing the loss function. And that is the optimization problem, where we minimize the average loss from each of the points. So in the case of the cancer study, we can choose two features. Let's say we choose the x to be area and concave points, and we try to find the hypothesis function h theta of x. If we know the parameters, then we can predict whether it's 1 or minus 1. So let's take this example. Suppose we found a hypothesis function h theta x. How would we interpret a new observation? Say we have a new observation with area 0.7 and concavity 0.5. Say we computed h theta x and got 0.7. We say that there's a 70% chance that the patient has a malignant tumor. So there are boundary issues with hypothesis functions. So in linear regressions, the outcome can be between minus infinity and plus infinity. But we need to classify and hence use a sigmoid function. We can bring outputs between 0 to 1. Then we can decide if output is greater than 0.5, then it is 1. If output is less than 0.5, then it is 0. So let's talk about non-linearizing the linear model. A good way to map a linear regression value that can be between minus infinity and plus infinity to a value between 0 and 1 is to use a sigmoid function. In sigmoid function, if x is greater than 0, then the function is greater than 0.5. And if x is less than 0, then the function is less than 0.5. As an example, let's assume that h theta x is 5.4. Now we get g of h theta x by plugging into this function here, the value of x to be 5.4 here. We get g of h theta x to be 0.99. And that can be classified as 1. What we note is that the function approaches 1 or 0 very quickly. So it's easier to classify something as 0 or 1. The area in the middle seems to be the gray area. So now we have a way to know how to classify a new observation using g of h theta x. Our prediction model is clear. We find h of theta x and then apply the sigmoid function. If the sigmoid value is greater than 0.5, then we take the prediction to be 1, otherwise 0. So here's another example. Suppose we know the theta values. Then for any new observation x1, x2, we can find the h theta x and determine if the value is greater than 0 or less than 0 by using the values of x and x2 and computing h theta x, and then taking the sigmoid value of the function. If the sigmoid function is greater than 0.5, then the classification is 1, otherwise it's 0. So we can use the same ideas with nonlinear boundaries. For example, we can have a nonlinear terms in a model like h theta x and apply g of h theta x, and if it's greater than 0, then it's 1, otherwise it's 0. Same way we can use separate a circle to separate the points here, using a model like minus 1 plus x1 squared plus x2 squared and applying gx to that. So how good is the classifier? We'll ask that question next. We can go with a simple loss function like 0, 1 loss function. In this function, we say if a sine h theta x, the predicted and the observed are the same, then we say that the classifier got it right. If not, the classifier got it wrong. So in this example, let's assume we are testing to see how well the classifier did it. If they have the same sign, here we use -1 and 1 to classify instead of 0 and 1, then the classifier got it right. In this shown example, you can see that the classifier got 4 of 7 right. Not a very good classifier. So there are other loss functions we can use, logistic, hinge, or exponential. One thing that notably differs between these losses is the scales to which they are affected by the outliers. For example, the logistic loss, if hxy is large positive number, then the loss is almost 0. Hinge loss or 0, 1 loss is the least sensitive to such outliers, as it suffers the same loss regardless of how confident the incorrect prediction is. Exponential loss is on the other extreme, with the loss function that increases extremely quickly for predictions that confidently correct. Now, in summary, here's how we compare linear regression model and logistic regression model. In linear regression, the hypothesis function leads to a value between -infinity and +infinity. In logistic regression, we do the same, but then apply sigmoid function to map the values to between 0 and 1. If the value is greater than 0.5, then we say it's 1, otherwise we say it's 0. So next we look at how to implement this using a real data set.